Alright guys, so this is the fall semester review. I'm going to split this video up into two parts because I just don't want to make a giant video for this. It's still going to be a lot of information anyway, but the whole purpose of this video is to help you with parts if you need it. If you want to watch the whole thing, that's great. If there's only certain areas that you need help with, you can always fast forward to those. You can rewind, so you can kind of go to areas that you need help on. Okay, so what I would recommend is I would have a calculator handy, and then also a periodic table and metric scale for this video. So that way, if you need to, you can pause it anytime and kind of work with me. So that way it's just right there and I'm not having to scroll back and forth between all these different things. Okay, so let's go ahead and start it off. So we're going to start off, and the very first thing was sig figs. So if we look at number 1 right here, it has 2300. So one of our rules was trailing zeros do not count if there is no decimal. Okay, so that means this 0 right here does not count, and this 0 right here does not count because there's no decimal. So this one just has 2. So going down to number 2, I will say this, do not worry about this right here. Okay, just focused on these numbers right here. So we have 8.10, there is a decimal, so that means that trailing 0 is going to count. So this has 3. Next one, so I'm not going to worry about this. I have 5.0, there's a decimal, so that trailing 0 is going to count, so this one has 2. Number 4, I have 1003, so any zeros that are in between non-zero numbers are always going to count. So this one would have 4 significant figures. Number 5, I'm going to go ahead and take this off. And then I have 2.110, there is a decimal, so that trailing 0 is going to count, so this one has 4 as well. Then I've got 8.0335. Okay, so zeros in between non-zeros always count, so this one is going to have 5 significant figures. Number 7, all right, so now we have leading zeros. Leading zeros never count, so I'm going to go ahead and mark those off. Then I have 230. Okay, so since there's a decimal, that trailing 0 does count, so this one's going to have 3 significant figures. Next one, I have 800.0. There is a decimal, so all trailing zeros will count, so this one will have 4. Then I have 0.0000. Okay, so I'm going to go ahead and take out these zeros because those don't count. Then I have 3400. There is a decimal, so those zeros count, so that is going to be 4 significant figures. Then I have 990.00. There is a decimal, so all those zeros will count, so this one has 5. Then I have 450. There is no decimal, so that 0 does not count. So this one only has 2. Number 12, I'm not going to worry about that. So 6.100, there is a decimal, so this one's going to have 4. Okay, so now we're going to go into mathematics. Okay, so what I'm going to do is I'm going to go through a few of these, just kind of show you how we kind of do it. Okay, so adding and subtracting, this is the way I do it. So I kind of take it back old school, kind of like elementary style. Okay, so what I like to do is I stack them. So I do 258.3 plus 257.11 plus 253. Okay, so this only works if your decimals are lined up. Okay, so what I'm going to do is I'm going to go ahead and do my math. So 1, 4, decimal goes right here. Okay, 7 plus 3 is 10, plus 8 gives me 18. Carry the 1. This gives me 16. Carry the 1. This makes me 7. Okay, so now what I'm going to do is I'm going to draw a line past my least accurate number. So the more decimal places you have, the more accurate you are. Okay, so 257.11 has 2 decimal places. It goes all the way to the hundredths place, so that is a very accurate number. 258.3 goes to the 10th place. Okay, so that's going to be a little less accurate. And then 253 doesn't even go into the decimal places. So that means I'm going to draw my line just past that 253. I have to stop past my least accurate number. Okay, so then what I'm going to do is I'm going to see this 4 is going to tell me if I round that 8 up or not. Okay, so if it is anything below 5, you're not going to round up. So my answer would just simply be 768 kilograms. Okay, so if you're going to do subtraction, it's going to be the same thing. You're just going to do 93.26 minus 81.140. Okay, so decimals are lined up. Okay, so I'm going to bring my 0 down here. 6 minus 4 is 2. 2 minus 1 is 1. 3 minus 1 is 2. And 9 minus 8 is 1. Okay, so I'm going to draw a line past my least accurate number. So 93.26, okay, is going to be my least accurate number because it only goes to the hundredths place. My 81.140 goes to the thousandths place. Okay, so I'm going to draw my line just past there. This 0 tells me if I'm going to round up. I am definitely not going to round up, so my answer would just be 12.12 centimeters. Okay, so adding, subtracting, you just kind of follow those rules. Okay, so I'm not going to go through all of these, okay, because some of these you can just do the exact same thing. Multiplying and dividing goes by a different rule. All you have to do is just count your number of sig figs. Okay, so you have 13.65. Okay, so that is going to have 4. Okay, you have 23.20. That is going to have 4 as well because there's a decimal there, so that trailing 0 counts. And 42.0, that is going to have 3. Okay, so you're only as good as your weakest link, so that means your answer can only have 3. So in your calculator, you're going to type that in. So 13.65 times 23.20 times 42.0. And that's going to give me this number right here. I get 13,300.56. Okay, but I can only have 3. Okay, so that means I've got here, here, here. So 1, 2, 3. I would draw my line. Okay, so this 0 tells me that I'm not going to round that up. So my answer would simply be 13,300. Okay, so you have to be careful with this. You cannot round that to 133. So 13,300 does not round to 133. Okay, so it is still 13,300, but we got rid of that 5 and 6 and that decimal place. Okay, so since there's no decimal place here, okay, these trailing zeros do not count. Okay, so this would just be 13,300 centimeters cubed. Okay, so dividing does the same thing. So you're just going to count sig figs. So 4.84 has 3. 2.4 has 2. So my answer can only have 2. So I'm going to type in my calculator. So 4.84 divided by 2.4 is going to be 2.01667. It just kind of goes on and on and on. But I'm going to count my 2. 1, 2, and I'm going to draw my line. This 1 tells me I'm not going to round that up. So my answer is just going to be 2.0, and my units is just going to be grams divided by milliliters. So since grams and milliliters have nothing to do with each other, all you got to do is just put them on top of each other. Okay, so multiplying and dividing, you just count significant figures and then go with the smallest number of sig figs. Okay, so one I want you to take a look at is anytime we have a parentheses, you will do the parentheses first. Okay, so remember PEMDAS. Parentheses always goes first. So what I'm going to do is I'm going to set this up. I'm going to do my adding. 8.807 plus 7.91. Okay, so I'm going to go ahead and do that. So I'm going to bring that 7 down, bring the 1. 9 plus 8 is 17. I'm going to carry that 1. Okay, so this is going to give me 16. Okay, so I have to draw my line past my least accurate number. So 7.91 stops at the hundredths place, so that's where I have to stop, is right there. This 7 is going to tell me that I have to round that 1 up, so this is going to be 16.72. So now you're going to do 16.72 times 5.3. Okay, so now we're doing multiplying, so we have a different rule. So we're going to do, so this one has 4 significant figures, this one has 2, so my answer can only have 2. Okay, so if you do 16.72, so give me 1 second. So 16.72 times 5.3. I get 88.616. Okay, so my answer can only have 2 significant figures. So I'm going to count 1, 2, draw my line. This 6 right here tells me I'm going to round up. So my answer would just be 89. Okay, so that is how you do math on there. So I'm not going to go through all of these. We have posted the keys, so if you need to reference those, you can do that. But this will just kind of help you with the rules and kind of give you a brush up on how to do that. Okay, so let's move on to the next page. So write the following quantities from scientific notation to ordinary standard notation with the correct number of significant figures. Okay, so first of all, I'm going to count significant figures. This has 6. Okay, so that means I have to have 6 in my answer. Okay, so if we have a positive exponent, that means this is a big number. So when I move my decimal is going to go to the right by 5. 1, 2, 3, 4, 5. Okay, so this is going to be 580,100. Okay, but if I leave that decimal off, I would only have 4 significant figures. I have to have 6 since I started with it. So I'm going to leave that decimal right there so those zeros count. So that would be your answer right there. Then you have 8.12 times 10 to the 7th. So this is going to be a big number because you have a positive exponent. So I'm just going to write this out here so I have more room. So 8.12 is going to go, so the decimal is going to go to the right by 7. So 1, 2, 3, 4, 5, 6, 7. And then I'm going to fill in everything with zeros. Okay, so my answer is going to be that. So it is going to be 81,200,000. Okay, I had 3 significant figures to begin with. I have 1, 2, 3 to end with because those zeros do not count. So that is going to be my answer right there. Okay, so part C, when you see a negative exponent, that means it's a really small number. So your decimal is going to go to the left. Okay, so I have 2 significant figures, so my answer still needs to have 2. I'm going to go to the left by 2. 1, 2. My decimal is going to be here now, and I'm going to add in that 0. So my answer is going to be 0.050 kilograms. Okay, so that has 2 significant figures as well, so everything's good. So 2.110, this has 4 significant figures. Okay, and this is a negative exponent, so it's going to go to the left by 3. 1, 2, 3. Decimals here now. I'm going to fill in my gaps. So my answer is going to be 0.002110 meters. Okay, so this has 4 significant figures as well because leading zeros do not count. So everything matches out. Okay, number 4. So now we're going the opposite way. So 5,800, that is going to be a big number. So that means we're going to have a positive exponent. So you're going to start from where the decimal would be. Okay, so it'd start right here. You're going to go to the left. 1, 2, 3. Okay, so you're going to stop right before that last number. Your number should always be a number between 1 and 10. So this is going to be 5.8 times 10, and however many you went over by. We went over by 1, 2, 3. So this is going to be a third power. Okay, and then this is meters, so we got to leave our units in. I only had 2 significant figures to begin with, and I have 2 to end with, so I am good there. So let's do another one of these. Let's jump down to C. Okay, so we're going to start from where our decimal would be. It would be right here, so we're going to go over 1, 2, 3, 4, 5, 6, 7, 8. So this is going to be 3.02 times 10 to the 8th meters. Okay, so I had 3 significant figures to begin with. I have 3 to end with, so everything is good there. Okay, so let's jump over to the smaller numbers. Okay, so I have a smaller number, so I'm going to start with a decimal, and I'm going to go to the right. 1, oops, don't know why it's doing that. Go over 1, 2, 3, 4. You're going to stop right past that first number. Okay, because it has to be a number between 1 and 10. That's going to be 5.08. That is a number between 1 and 10 times 10, and however many we went over by. We went over by 1, 2, 3, 4, and that is going to be a negative 4 since we're a small number. And we're going to leave our units in, and then we're good. So we had 3 significant figures to begin with. We have 3 after, so we're done. Okay, I'm going to do the next one. So I'm going to start my decimal. Go 1, 2, 3, 4, 5, 6, 7. So this is going to be 4.50 times 10 to the negative 7 kilograms. Okay, so I had 3 significant figures here. I have 3 here, so I am good to go. Okay, so that was just kind of a brush up on how to do the scientific, going forwards and backwards. So going from scientific to standard, and then going from standard to scientific. Okay, so dimensional analysis. Okay, so we're going to do some of these. So you would need your metric scale handy for this one. Okay, so we're going to go ahead and start on that. Okay, so 360 centimeters. So the very first step that I do, the way I do this is I'm going to do it through dimensional analysis, which is this way. So 360 meters, and then I'm going to draw my line. Okay, so that is the first step I do, is I always write out what is given. Okay, so before I even worry about numbers next, I know that centimeters has to be on bottom next. So in order for those to cancel out, they would have to be on bottom next. Okay, so centimeters, we can go from centimeters to nanometers since this is just a simple size shift. Okay, so you're going to look, so the way I do this is you're going to look at your metric scale, and you're going to see which one's bigger. Okay, so centimeters is going to be bigger. Okay, so centimeters is going to be 10 to the negative 2. Nanometers is 10 to the negative 9. Okay, so centimeters is bigger, so I'm going to set that as 1. So if you set your biggest one as 1, and then just count how many spots it takes you to get from negative 2 to negative 9. And that would be 7. So this is going to be 1 times 10 to the 7th power. Okay, so the centimeters cancel out. I'm in nanometers, which is what it wanted. And so now I'm done. So anything on top, you always multiply. Anything on bottom, you would divide. So we're going to do 360 times 1 times 10 to the 7th. Okay, so this is where you got to be careful on your calculator. If you're going to do 1 times 10 to the 7th, actually typing out the 1 times 10 to the 7th with the exponents and everything, I would make sure to keep things in parentheses. Otherwise, your calculator can get a little bit wonky. Okay, so I get a really big number. Okay, so I'm just going to go ahead and convert that to scientific mode on my calculator. So let me switch that. And I get 3, pen shut off. I get 3.6 times 10 to the 9th nanometers. Okay, so I had 2 significant figures to begin with. Okay, so I have to have 2 to end with, so everything is good there. Okay, so however many significant figures you start with, better be what you end with. Okay, so next one, part B, we're going to do 600.0 megahertz to hertz. So we're just going to start off with what we're given. So 600.0 megahertz. So this is going to be a big M. So MHz. Okay, so that's my first step. Next thing is I'm going to bring this megahertz down to the bottom. And then I'm going to have hertz on top. Okay, so I'm going to look on my metric scale. Megahertz is going to be 10 to the 6th power. And hertz is a base, which is 10 to the 0. Okay, so that means megahertz is going to be bigger, so I'm going to set that as 1. And then I'm going to count how many spots it takes to get from 6 to 0, and that's going to be 6. So 1 times 10 to the 6th. So now I'm going to do is just multiply that, so 600 times 1 times 10 to the 6th. And I get 6.000 times 10 to the 8th. Okay, so the reason why, and this is in hertz, so we're done there. The reason why I have so many zeros is because I had 4 significant figures to begin with, so I need to have 4 in the end. Okay, well, so we'll do one more of these. So I have 3.4 millimeters to kilometers. So 3.4 millimeters. Okay, so that's my first step. I'm going to bring millimeters down here. Okay, and that means kilometers is going to go on top up here. So we're going to see which one is bigger. Okay, so millimeter is 10 to the minus 3. Kilometer is 10 to the plus 3. So that means kilometer is bigger, so we're going to set that as 1. And then I would count how many spots it takes me to get from kilo to milli, and that's just going to be 6. So this would be 1 times 10 to the 6th. Okay, so now it's on bottom, so we're going to take 3.4 and divide it by 1 times 10 to the 6th. So 3.4 divided by 1 times 10 to the 6th. And I get 3.4 times 10 to the negative 6th. And this is kilometers now, and that is your answer. Okay, so this is the way. There's multiple ways to do this, but this is the way that I found is most easiest, using your metric scale, so you will get that on the exam as well. Okay, so let's go over to the next page. There may be a little bit more. Okay, so this is basically just the same thing. So if you need help with that, you can refer to the key, and you can kind of go back and watch those other examples. Number 6, give the measurements for each of the following using the correct number of significant figures. Okay, so that when it comes to measuring, significant figures is we have to go one more decimal place than you can see. Okay, so if I were to look at this, so a normal person would look at this without knowing about significant figures, you would just tell me this is 3 centimeters. Okay, so it stops at the ones place. All we see is 3 centimeters. Significant figures states that we need to go 1 decimal further than you can actually see on the measuring device. Okay, so if you think this is 3 on the dot, you would need to put 3.0 centimeters. Okay, so the point is I can't see the 10th place, but that's where you have to take it. Okay, so you can put 3.1 centimeters if you think it's 3.1. You can put 2.9 centimeters. Okay, if you think it's 2.9, so it's just kind of relative. So you're not necessarily going to be wrong. Okay, so unless you're way off and you just tell me 2, okay, like 2.0, but you have to take it 1 decimal place further than you can see. So let's look at the next one. Okay, so this one looks like it lands right about 4.8. Okay, so if you were to tell me 4.8, okay, this would be wrong. Okay, because I can see 4.8. So I need to take it 1 decimal place further. Okay, so I'm going to start going into the hundredths place. So if you think this is 4.8 on the dot, just put 4.80. Okay, so you could put 4.81. You could put 4.79. Okay, so whatever you kind of think it is, but the point is I took it to the hundredths place at that point. Okay, so we're going to move on to the next one. So we're going to compare and contrast accuracy and precision. Okay, so accuracy is simply how close you are to the target. Oops. And the keys are going to be a little more in depth. I'm just kind of going over these in general, going over the main points that you need to know. Okay, so accuracy is just how close you are to the target. Okay, so if you hit the bullseye, you are considered accurate. Now, precision. Okay, so precision is how close the measurements are to each other. And kind of bear with my handwriting here. How close the measurements are to each other. Okay, so if I had a bullseye, okay, so I'm going to draw, this is going to probably be a bad one. Okay, because I'm kind of in my truck right now doing this late at night, so I don't wake up my son. Okay, so here's my target. So accuracy would be like if you could land it right in the middle, that would be your accuracy. Okay, so if you landed all around it, kind of like this, and your average came out to a bullseye, you would be considered accurate. Precision is like if I was over here and all my shots were right around each other. That is precision. So if all my shots are close to each other, I'm very precise. I don't have to be accurate to be precise, as long as my shots are close together. Okay, so you can be precise and accurate. If you had all your shots landed right around the bullseye, that would be precise and accurate. Okay, so accuracy is how close you are to the target value. Precision is how close your measurements are to each other. Okay, so those don't necessarily have to be accurate. Okay, so there goes that page. So we're kind of moving through this. So that's good. Okay, so now we're going to move on to going to states of matter. Okay, so we're going to go over gas, liquids, and solids. Okay, so the shape of a gas would be considered, so let me zoom in a little bit on this. Okay, would be considered indefinite. Oop, don't know why this is glitching out on me. So indefinite. Okay, because gas can take the shape of anything. Okay, so it can take the shape of any container. Its volume is going to be indefinite. Because again, it can kind of take the shape of any container. Okay, particle spacing and compressibility. Okay, so it is going to spread out because gas it's very small, so it just takes up and kind of moves on, just takes up its container and moves on. So it's not really dense around each other. Okay, and it is also very compressible. So since there's so much space in between, there's a lot of room to compress it. Particle movement, this is going to be considered rapid. Okay, so gases are very fast moving molecules. Okay, and diagram of the molecules is just going to basically be a bunch of gas particles kind of moving around at high speeds. Okay, so pretty spread out. So then we go over back to our liquid. Okay, so liquid shape is going to be indefinite as well. So if you pour a liquid into a container, it will take the shape of the container. Okay, volume is going to be definite. Okay, so if I pour water into a container half full, it's not going to expand and take up the whole container. So it does have a definite volume. It will stop at some point. Okay, so it will not spread out to take over the whole container. Okay, particle spacing. Okay, so it's going to be a little more compact than gas. Okay, so it's going to be a little bit more dense. And then as far as compressibility, most of it's going to be incompressible. You can compress it to a certain extent, but you will quickly run out of space to compress. Okay, particle movement. Okay, so this is going to be less than gas, but more than solid. So you do have a little more movement in a liquid than a solid, but not as much as a gas, but more than solid. Okay, diagram of that is just going to be molecules. They're just going to be a little bit more closer together. Okay, so this is just kind of the gist of it. Okay, a solid, it is going to have a definite shape. Okay, if I take a coin and I throw it into a container, the coin's not going to mysteriously just take the shape of its container. It is stuck in the shape that it is in. Okay, its volume is going to be definite. Compressibility and compact, so it is going to be very compact. So a lot more so than liquid. And not very compressible, so this is going to be incompressible. Okay, particle movement, this is going to be very slow. Okay, so everything's so close to each other, there's not a whole lot of room to go. Okay, so it's going to be very slow movement. So my particles are going to look like this. They're going to be pretty much stacked right on top of each other. Okay, so a lot of this should be a lot of you even from elementary school, middle school, things like that. So that is just kind of a refresher. Okay, so number 9, for each of the following statements, indicate whether it refers to a solid, liquid, or a gas. Particles vibrate in place. Okay, so that means there's not a whole lot of movement there, so that is going to be a solid. Particles are moving past each other at high speeds. So that means we're dealing with gas. Okay, so gas particles, they have a lot of room so they can pick up speed. Particles are close together. but are able to move past each other. Okay, so this is going to be a liquid. Okay, so they're closer together, but there is more room to move around than a solid. The state of the matter that is most compressible, this is going to be a gas, so since there's all that space in between the particles, you can compress it more. This state of matter has definite volume, but indefinite shape. This is going to be liquid. Because remember, liquid can take the shape of its container. And this state of matter is the most dense. This is going to be a solid. Number 10, draw the flow chart for the types of matter. Include terms matter, pure substances, mixtures, elements, compounds, homogeneous mixtures, and heterogeneous mixtures. Okay, so we have matter. Okay, which is everything is composed of matter. Okay, that is going to be broken down into two things. You have substances and you have mixtures. Okay, so we're going to start with our substances. Substances can be broken apart into elements, which you get plenty of practice on that on the periodic table. Okay, and then you get compounds. Okay, which we still use the periodic table to form compounds. Okay, so elements is just an element by itself. So that would be like oxygen, hydrogen, and these are going to be inseparable. Okay, so these are going to be inseparable. And compounds would be something like H2O, CO2, and this would take more of a chemical separation. So it can be separated, but through a chemical reaction. Okay, so then we're going to go back over to mixtures. We have two types of mixtures. Okay, we have homogeneous. Okay, and we have heterogeneous. Okay, so homogeneous is going to be where it kind of mixes together and you can't really tell the difference between the different particles that are in it. Okay, so that would be kind of like things like milk, things like that. That would be, there's different things in it, but it looks like a uniform liquid. Heterogeneous mixtures would be something like trail mix. You can see the different particles in it, so even though it's kind of blended together, you can still see the different parts of it. And these would both require a physical separation. Okay, so moving on. So that was number 10, so we're going to move on to number 11. Okay, so number 11, label each model as an element, compound, or mixture. Okay, so if I have these small particles and I have big particles, this is going to be a mixture. Not a compound, because they're not actually bonded to each other. It's not one element, because we can see that there's different things in there, so that's going to be a mixture. Then the next one I have, it looks like elements that are bonded to other elements. Okay, and this would be a compound. Then I have, it looks like one uniform substance. Okay, so there's no differing particles in there, so this would be an element. And then lastly, it looks like we have some compounds and elements in there, so that is going to be a mixture. Okay, number 12, types of matter. Explain the difference between an element and a compound and give two examples of each. Okay, so we kind of just talked about that. So an element, so they're both pure substances. Okay, but elements are by themselves. Okay, so this would be like hydrogen, carbon, fluorine. Okay, so that means they're just by themselves. A compound is when you start dealing with two or more atoms. Okay, so two or more atoms. An element is just one atom. Okay, so a compound example of that would be like CO2 and H2O. And B, explain the difference between heterogeneous mixture and homogeneous mixture and the separation techniques that can use for each. Okay, so we kind of just talked about that again. So heterogeneous means it's not blended. That means you can see the different particles kind of all throughout it. Homogeneous is going to be well blended. Okay, so this is going to be kind of a constant composition. Okay, so if you take sugar and dissolve it in water, so sugar and water. Okay, so the sugar is going to dissolve to the point where you can't really see it anymore. It just still looks like water. Okay. But a heterogeneous mixture would be like if you were to drop particles in water, like big chunks of dirt, things like that, and they don't dissolve, you can kind of still see it floating around. That'd be a heterogeneous mixture. Okay, sorry, I had to kind of take off my jacket there. So 13, we're going to move on to 13. So an intensive property. So we're going on to intensive properties, extensive properties. So the big thing with intensive properties is the main thing you need to know is that it does not depend on the amount of substance. So it does not depend on the amount of substance. Extensive does depend on how much there is. So it does depend on amount of substance. Okay, and we're going to get into examples of that here in a second. So we're going to go on to physical property. So physical property is just a property which can be measured without altering the actual material. Okay, so it can be observed. Okay, so kind of messed up there. Can be observed without altering the substance. Okay, so that'd be something like looking at what color it is. I don't have to change it, okay, to notice that the color is a physical property. Okay, and let me jump over here. So chemical property is observed when a chemical reaction occurs. It's observed when a chemical reaction occurs. So that means we're actually changing up the substance. So that means we're moving it, it's being morphed into something else. A physical change, okay, is just basically a change which changes only the physical property of the material. Okay, so only changes the physical property. Okay, so that means that'd be something like melting an ice cube. Okay, so we changed the physical property of it, but then we didn't change it to anything else. It's still water before and after. And then chemical change, okay, that is when we actually rearrange into a new substance. Okay, so that means we're actually going to change it into a new substance. Okay, so changes into a new substance. So now we're going to do some examples. Sorry. Okay, so if we were to look at color, okay, color does not matter. It does not matter how much there is, so it's still going to have the same color, so this would be an intensive property. Is it physical or chemical? This would simply be physical because it's just color. Combustibility, okay, so that means the likeliness to it, basically the ability to explode. Okay, so it does not matter how much there are. Okay, that is going to be an intensive property. Now, combustibility is a chemical reaction, so that means you will change the substance. So this would be a chemical property. Hardness does not depend on how much there is, and this would be a physical property. Density, okay, things have certain density, so it does not matter how much there is that would affect density. So density would be intensive property, and this would be a physical property. Now mass does care about how much there is. Okay, so like I have a different mass than a small child would. Okay, so mass does care about how much there is. So this would be extensive property, and this would be physical. So we're just looking at it, we're not changing anything. Melting point. Okay, so things are going to have certain melting points, so that is going to be an intensive property. Doesn't matter how much there is. And this is going to be physical, so just because we're melting something doesn't mean we're actually changing it. If we were burning it, that would be different. Let's see, ductility. Ductility is just the ability to basically draw into wires for electricity, things like that. And this is going to be an intensive property. And then ductility is going to be a physical property. Okay, volume. Volume, we do care about how much there is. So this is going to be extensive. Okay, and volume is going to be a physical property because we're not actually changing anything. Okay, reactivity with acid. Okay, so it does not matter how much there is. This is going to be intensive. But anytime you see reactivity, okay, so that means something's going to change, which means this is going to be a chemical property. Odor, that is going to be intensive. Doesn't matter how much it is. Still going to have the same smell. Okay, and this is going to be physical. Nothing's changing. Weight, this is going to be an extensive property. Okay, so just like when you gain weight, it does care about, okay, the scale cares about what you're eating, about adding more and more substance, so your weight is going to change, so that is extensive. And this is going to be physical because we're not changing anything. Malleability is just the ability to basically bend it. Okay, this is going to be intensive. Doesn't matter how much there is, and this is going to be physical. And then tendency to corrode, so basically the tendency to rust, things like that. This is going to be intensive. And once you corrode, you are changing the substance, so this would be a chemical property. Okay, describe the 5 evidence of a chemical change. 5 evidences of chemical change. So 1 would be light is created. Okay, 2, you have heat is produced or even absorbed. Okay, so if your actual substance gets colder, so it actually absorbs that heat, that is going to be a chemical change. So 3, if we have gas created, so gas is created, that is going to be a chemical change. Okay, so color change. So remember we said color was a physical property, but if we're changing colors, that would be an example of a chemical change. Number 5, we have a precipitate is formed. A precipitate just means a solid. Okay, so if I were to add 2 liquids to each other and they create a solid, that is a precipitate. So that is a chemical change. And just another one, if we're basically creating electricity, okay, that would be a chemical change as well. Okay, so now let's move on to 16. Okay, I believe that's down here. Okay, number 16, classify the following changes of matter as physical or chemical and provide evidence for each. Okay, so an ice cube is melted. Okay, so this would be a physical change because we didn't do anything. Okay, so still water. Okay, so we just changed the state of the matter. We didn't actually change the actual substance itself. Okay, sugar dissolved in water. This is going to be physical. We're not altering anything. Okay, and it's still sugar and water. Okay, so we didn't really do anything. So we're not really making anything new out of that. We're just kind of dissolving them and blending them together. Baking soda reacts with vinegar and forms a gas. So there's your key word right there, reacts. Okay, so when you have a reaction, that is going to be a chemical change. Okay, and how would we know there was evidence? Because you have gas being formed. Okay, a piece of copper wire is bent in half. So this is going to be a physical property. So we didn't change the wire. Okay, so nothing new. So still wire. Okay, so still copper wire. We didn't change the element itself, so we just bended it. Okay, an aspirin is crushed into fine powder. This is going to be a physical. Okay, because all we did was crush it, so it is still aspirin. Copper turns green when exposed to environment. So this is corrosion. Okay, so this is going to be chemical. Okay, so we're actually changing it, and so this would be a color change, would be one of those hints that it is a chemical. Okay, chemical change. Two clear liquids are mixed and a yellow cloudy substance forms. Okay, so we're creating a precipitate there. Okay, so that's going to be a chemical changed. Okay, so we're creating a precipitate, a solid out of two liquids. A tree burns to form ashes. This is going to be chemical because we can't go back. Okay, we're changing the tree into ashes. Okay, so this is going to be a new substance now. A piece of paper is crumbled. This is going to be physical. Okay, so this is still paper. Okay, so sorry, it's kind of hard writing on this because I can't touch it with my hand, because otherwise it tries to switch this up a little bit. It tries to change the photo. Water freezes to form ice. This is physical, so still water. Okay, a candle burns. This is going to be chemical, so we are changing, so we have a new substance. Okay, so hopefully you're kind of getting the point of this now. Okay, so physical and chemical. So let's go ahead and move on to the next part. Okay, which is going to be our scientists. Okay, so Dalton. So his thing was his 5 postulates. He was the father of atomic theory. His 5 postulates. So one was atoms are indivisible. Okay, we proved that that was wrong. Okay, because we could actually break those apart. You can break it down into a proton, electron, and neutron. Okay, his second postulate, atoms are indestructible. So we can't break it down. Okay, so we can't actually destroy it. But when we actually look at things through like decay, things like that, we can actually break that down. So that one was disproven as well. Number 3, okay, all atoms of an element are the same. Okay, we figured out that this was wrong. Okay, so the first 2 are kind of the same thing. Okay, the third one, all atoms of an element are the same. Okay, so we figured that that was wrong because you have things like isotopes. So you have things like carbon-12, carbon-13, carbon-14. Okay, they're all still carbons, but they are different. Okay, then for atoms that are different, are different. So that one's pretty self-explanatory. That one still sticks. Okay, and then lastly, atoms combine to form compounds. Okay, so his big thing was the 5 postulates. So he was one of the first ones. Okay, so that's why his model was considered the billiard ball model. Okay, so he thought the atom was just one nice, perfect ball, and that was it. Okay, then you had J.J. Thomson come through, so he used the cathode ray. Okay, and he discovered the electron. Okay, so his model was you had this atom, okay, which was basically all positive. Okay, but then you had little negative electrons kind of floating all throughout it. Okay, so his was called the plum pudding model. Okay, then you have Rutherford. Okay, so let's go back to my color. Okay, so then you had Rutherford, so he did the gold foil experiment. Okay, so he fired a bunch of positive particles at a piece of gold foil. Most went through, but some bounced back. Okay, so gold had a positive charge, so if something was bouncing back, that meant that it had to run into something positive as well. Okay, so he discovered the positive nucleus. Okay, So his model kind of looked like this. So he still had the nucleus. So you had like this atom that had a nucleus now. And this was all positive. Okay, and then you had little electrons just all kind of floating around it randomly. Okay, so they could be anywhere. Okay, so these are all electrons. Okay, then Bohr came along and basically stated that electrons had to be on energy levels. Okay, so they weren't just randomly floating around. So you had the nucleus, the positive nucleus, but then you had electrons that would be on these energy levels. So like these rings that look like this. So electrons would be on these energy levels. So not just randomly floating around, but that is where they had to be. Okay, and the quantum mechanical model. So basically what that did is it just kind of made sure that, so it wasn't just nice kind of flat rings that just kind of floated there. It was electrons that were in three-dimensional orbits. Okay, so electrons. See, there's kind of messed up again just because I touched it. Electrons are in 3D orbits. Okay, so that means we still have our nucleus, our positive nucleus, but electrons just kind of create this cloud all around the nucleus. Okay, so they're still on those energy levels. Okay, but they're not just in perfect circular orbits. Okay, so they kind of move in three-dimensional shapes. And we can kind of tell where the probable location of the electrons would be. We don't know exactly where they would be, but kind of probability where they would be. Okay, number 18. Okay, so we're going to do average atomic mass. Okay, so this is just kind of some simple math. Okay, so the key to doing this is we're going to just multiply each mass by its percentage. Okay, but you have to be careful. So 63.929 times 48.89 is going to give you a really big number. So you would need to convert this to decimal form. So all you have to do is move the decimal to the left by 2. So this is going to be 0.4889. This would be 0.2781. This would be 0.0411. This would be 0.1857. And then you get 0.0062. Okay, so all you're doing is you're multiplying across. Okay, so 63.929 times 0.4889. Okay, and let me switch out of scientific mode real quick. Okay, and I get 31.255. Okay, then I'm going to do 65.927 times 0.2781. That's going to give me 18.334. Then I'm going to do 66.927 times 0.0411. Okay, and that gives me 2.751. 67.925 times 0.1857. And that gives me 12.614. And then lastly, 69.925 times 0.0062. And that gives me 0.434. So now that I have all those individual numbers, we're just going to add those up, and that would be our answer. Okay, so 255 plus 18.334 plus 2.751 plus 12.614. Sorry. 12.614, sorry. Plus 0.434. And I get an answer of 65.388. So that is going to be my average atomic mass right there. Okay, so all of these individual masses, so like here, 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 these are all isotopes. Okay, so these are all zincs, but they're different because of their number of neutrons. Okay, so that you can see clearly that zinc 70 is not very common. It only happens 0.62% of the time. Okay, versus zinc 64, that's going to happen in nature 48.89% of the time. So that's going to be a lot more common. Okay, so part B, all you would do is take your mass numbers. You're going to do the same thing. So you would just take 28 times 92.21, get a number. You're going to do the same thing we did in the last problem. And then once you find your mass, okay, so I believe I have it down right here. So once you did the math, you would get 28.1 AMU. That just means atomic mass unit. So you would look on the periodic table and see which one has an atomic mass of 28.1, and that would be silicon. Okay, so you do the exact same thing as we did in part A, and then you would look up the mass on the periodic table. Okay, so let's move on to 19. So this is where you're going to really need a periodic table handy. Okay, so we're going to fill out this chart. So first we're going to start off, we're going to do oxygen. So oxygen 18, so this is hyphen notation. Okay, so that 18 is going to be the mass number. Okay, symbolic notation is where you just take the element, so the symbol, so oxygen. Mass number goes on top, and then the atomic number or number of protons goes on bottom. Okay, so if you look up oxygen on the periodic table, that has an atomic number of 8, so 8 is going to go on bottom. You can fill in 8 right here. Okay, the mass on the periodic table would be 15.99. The number of protons is simply the atomic number, so that's going to be 8. Okay, electrons, if there is no charge, it's just going to be equal to the protons. So if I have 8 protons, I'm going to have 8 electrons. Neutrons is just the mass number minus the number of protons. So you would take this top number, 18, so right here, 18 minus 8, and that is going to give me 10 neutrons. Okay, then is it neutral, a cation, or anion? So since there's no charge, this would be neutral. Next one, we have 21383 Bi3. So Bi is going to be bismuth. And when we do hyphen notation, it's bismuth dash the mass number, which is 213. Atomic number is 83 because that's the number on bottom. The mass on the periodic table is going to be 208.98. Your mass number, they already told us that. That's the number on top, so that was 213. Protons is just your atomic number, so that's 83. Electrons, so if this was neutral, it would be 83. But we have a negative charge. When we have a negative charge, that means we gained electrons. So since electrons are negative, that means we gained 3. So this would be 86. Okay, neutrons, you would just take your top number minus your bottom number. So 213 minus 83 gives me 130. And this has a negative charge, so this would be an anion. Okay, the atomic number 23. So if you look up 23 on the periodic table, that is going to be vanadium. Okay, so vanadium dash, and my mass number is 50, so that's what they gave me. Okay, so my abbreviation for vanadium is just V. My mass number goes on top, so that's going to be a 50. And my atomic number is going to go on bottom, so that's a 23 right there. So do not worry about charge. We would give you a charge, so you do not need to create a charge for yourself. Okay, vanadium has a mass of 50.94 on the periodic table. Protons is just the atomic number, so that's 23. There is no charge, so protons and electrons will be the same. Okay, my top number, 50 minus 23, is going to give me 27 neutrons. There's no charge, so this would be neutral. Okay, next one, we have 2512 Mg2+. So Mg is going to be magnesium dash the mass number, which is 25. Okay, so my atomic number is the bottom number, so that's going to be 12. Okay, the mass of magnesium is 24.31 on the periodic table. My mass number that they gave me was 25. My number of protons, okay, is just the atomic number, so that's going to be 12. Okay, electrons, so this is not a neutral atom, so it's not going to be 12. So since it's a +2, that means I have more protons than electrons. So that means I lost electrons. Okay, so it's going to be the opposite of what you think. Everyone wants to add 2, but it's the opposite. So that means I have 2 more protons than electrons, because protons have a positive charge. So 12 minus 2, that means there are 10 electrons. Neutrons, I'm just going to take my top number minus my bottom number. So 25 minus 12 is going to give me 13. And since it has a positive charge, this would be a cation. Okay, so hopefully that kind of helped you out a little bit there. I'm not going to go through the other 3 because we'll try to move on. 20, give the pin number. So pin just means proton, electron, neutrons. Numbers for each of the following ions. Okay, so zinc. So Zn with a +2. Okay, so you're going to need your periodic table. Okay, so I'm going to grab mine real quick. Let me find it. Okay, so zinc has an atomic number of 30, so there's my number of protons. Okay, my electrons, if this was neutral, it would be 30. But since I have a positive 2 charge, that means I'm missing 2 electrons, so that's going to be 28. And my neutrons, okay, is going to be, sorry, I need to get a drink real quick. Okay, so you would have to look up your mass number on the periodic table. Okay, so zinc has a mass number of 65.38, so basically 65. Okay, and then you're going to subtract that minus your number of protons. So that means it has 35 neutrons. Okay, so we're going to move on to phosphorus. So we have a P with a -3 charge. Okay, so phosphorus has an atomic number of 15. Okay, I have a negative charge here. Okay, so that means I have extra electrons. So that means this would be 18 electrons. And phosphorus has basically a mass number of 31. Okay, you can find that on the periodic table. It's just the mass of it. So 31 minus my proton, so 31 minus 15 is going to be 16 neutrons. Okay, so hopefully that kind of helped out a little bit. Okay, so we're going to kind of move on to the next section. So let me get back over to my thing. Okay, so we're going to move down. Okay, 21, complete the following table for each of the types of radiation. Okay, so we're going to kind of go through these fairly quick. So alpha, remember alpha is going to be the 4-2 helium, or it can be the little fish symbol. Okay, beta was the 0, -1e. Okay, or you could do the B with a little tail. Either one. And then gamma was just the 0, 0, y. Okay, so the charge of an alpha would be +2. So the main thing you need to know is that alpha has a positive charge, beta has a negative charge, and gamma has no charge. Okay, the mass, so since you're dumping off a helium has, so this 4, that top number is my mass number, so that means it has a mass of 4. Beta, since it's basically dumping off electrons are so small that your mass really is negligible. So it really doesn't matter because it's so small. And gamma has no mass. It's basically just energy being emitted. Okay, so penetration, alpha, remember, so alpha is the lowest energy. Okay, so it has very low penetration. So I think a piece of paper would be able to stop it. Beta is going to be very medium energy. Okay, so medium energy, so that means it's going to have a medium penetration. Okay, and that would take aluminum foil. Okay, so I'm just going to kind of write out here instead of drawing it out. Okay, so aluminum could stop it. Paper could stop alpha. Okay, and gamma is going to be very high energy. Okay, which means it's going to have a high penetration. Okay, so that means it would take a lot of lead to actually stop that. Okay, so 22. Compare and contrast fusion and fission. Okay, so the main thing you need to know about fusion and fission. Okay, fission is when you break something apart. Okay, and fusion is when you combine together. Okay, they both produce a lot of energy. Okay, fission is usually found in nuclear reactors. Okay, so that's when we're breaking apart things like uranium. Okay, but it is very radioactive. Okay, fusion is when we combine hydrogens to make helium. Okay, so now I could write out a lot this more in depth, but we have that on the key. Okay, so I'm just kind of explaining the gist of what you need to know. Okay, so going down to 23, so we're going to look and see what types of decay this would be. So we have a 4,2 helium, so right now we know this right off the bat is alpha. Okay, so the big thing is you have to make sure you have the same numbers on the left side of the arrow as you do on the right side. Okay, so if I have 86 on the left side, I need to have 86 on the right side on the bottom. So what plus 2 gives me 86? So that means 84 is going to be on bottom. I have 222 on the top left on the left side, and I need to have 222 on the top on the right side. So what plus 4 gives me 222? This will be 218. Okay, and since I have a new atomic number, so that 84 is different than 86, this is now polonium. Okay, the next one I see is 0, -1e. This is going to be beta. Okay, so I have 82 on the bottom on left. I need to have 82 on the bottom on right. So what minus 1 gives me 82? So that means that's going to be 83 on bottom. Your mass doesn't change in beta, so I'm just going to keep 214 on top. And 83 is going to be bismuth on your periodic table. Okay, the next one I see 0, -1e, so this is going to be beta again. I have 14 on bottom on the left, so I need to have 14 on bottom on the right. So what minus 1 gives me 14? Okay, so that's going to give me 15. Okay, my mass didn't change, so I'm going to keep that as 27 on top. Okay, and 15 is going to be phosphorus. Okay, so now we don't have a particle, but we can find out what it is. I have 83 on the bottom on left, and I have 81 on the bottom on the right. I need to get it to 83. So what plus 81 gives me 83? So that would be 2 on bottom. Okay, I have 214 on the top on the left, and I have 210 on the top on the right. So what plus 210 gives me 214? So that would be 4. So this is going to be the 4,2 helium. So this was going to be alpha. Okay, the next one, we don't have the particle. So we need to figure out what it is. I have 92 on bottom on left. I have 93 on the right. So I need to know 93, how would I get from 93 to 92? I would have to subtract 1. So 93 minus 1 would give me 92. My mass number didn't change because it's 234 on both sides. So I'm going to put a 0 on top. So this is going to be beta. Okay, and last one, I have a 6027 calcium and a 6027 calcium, so nothing changed at all. Okay, so this would be a 0, 0. So that means this one would be gamma. Okay, so I think that was it on that one. Okay, so let's go over here. So write the balanced nuclear equation for beta decay of the following. So we're doing beta decay, so that means we're doing the 0, -1e. Okay, so the first thing we need to do is we need to convert carbon 14 into basically the isotopic notation. So it would be C with a 14 on top, and carbon has an atomic number of 6. So that is how you convert it from the hyphen notation to isotopic notation. Okay, so we know it's going to be beta, so we're going to go ahead and draw our arrow with a 0, -1e. Plus, we need to figure out what it's going to change into. Okay, so what minus 1 gives me 6. So that means 7 is going to be on bottom over here. And I have a mass number that's not changing on top up here. Okay, so now I look up 7 on the periodic table, and that is going to be nitrogen. Okay, let's do the next one. I have strontium 90. So strontium is Sr. I'm going to put 90 on top. Okay, and strontium on the periodic table is going to be 38. Okay, so this is going to be the same thing. So we're going to do a 0 -1e. So what minus 1 equals 38? So this is going to be 39. My mass number didn't change, so I'm going to keep 90 on top. And then this is going to be yttrium. Okay, let's go ahead and jump on to alpha. Alpha is going to be the 4,2 helium. Okay, so we're going to first convert it. So we have thorium-234. Okay, so thorium is Th. We're going to put 234 on top. Okay, and thorium has atomic number of 90. Okay, so we're going to draw our arrow, and this is going to be a 4,2 helium. Okay, plus we need to figure out what it's going to be, what's going to be changed into. Okay, so I have 90 on the left on bottom. I need 90 on the right 90 on the bottom on right. So what plus 2 gives me 90? So that's going to be 88. Okay, so I have 234 on top on the left. So I need 234 on top on the right. So what plus 4 gives me 234? So that's going to be 230. So now I would look at 88 on the periodic table, and that is going to be radon. Okay, let's do the next one. Radium. So that is going to be Ra, and with a 222 on top, and radium has atomic number of 88. Okay, we're going to go ahead and do our alpha particle. So that's going to be a 4,2 helium plus blank. Okay, so I have 88 on bottom on the left. So I need to have 88 on bottom on the right. So what plus 2 gives me 88? So this is going to be 86. I have 222 on top on the left. I need 222 on top on the right. So what plus 4 gives me 222? So this is going to be 218. Okay, and 86 on the periodic table, okay, is going to be Rn. Okay, so that is going to be the radon. Okay, so let's move on to the next. Okay, number 26. How are the mass and atomic number of the nucleus affected by each of the following particles? Okay, so basically when we kick off an alpha particle, which is the 4,2 helium, okay, our mass is going to decrease by 4, okay, because we got rid of a mass number of 4. And since we're dumping off a helium that has an atomic number of 2, your atomic number will decrease by 2. Okay, a beta particle, that's when we do the 0 -1e. Okay, so if I have no mass, okay, electron basically has no mass, mass would be unchanged. Okay, and then I'm dumping off a negative particle. Okay, so that basically is going to give me a more positive charge. So my atomic number is actually going to go up by 1. Okay, so number 27, draw and explain Aufbau's principle. Okay, so Aufbau's principle is when we did this, it was the 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f, 6s, 6p, 6d, oops, messed that up, 6d, and then you had 7s and 7p. Okay, and then we drew the arrows through it. So we had to start at 1s, and then we went to 2s, then we went to 2p, then 3s, then we went to 3p, then 4s, and then 3d, 4p, 5s. So you kind of get the gist of that now. Okay, so that is basically the order of energy levels. Okay, so that means you have to fill in the lowest energy level first before you move on. Okay, so you would have to fill in 2p before you move on to 3s. You would fill in 3p before you move on to 4s. Okay, so you have to fill in the lowest energy level first before you move on. Okay, so in our key has a little bit more in depth on there if you need more explanation there. Okay, so number 28, complete the following table using the periodic table. Okay, so we gave you the noble gas electron configuration. So remember your noble gases, this is when you need the periodic table. Okay, so your noble gases is that last group on the right. Okay, so starting with helium and going down. Okay, so the noble gas shortcut was just a way that you could start there and then go down to the next level instead of having to start all the way at 1s and then doing 2s, then 2p, yada, yada, yada. Okay, so if you look at your periodic table and you start at neon, go down to the next level. Okay, so you read it just like a book. So you have to go down to the next sentence, basically. Okay, and you read a sentence from left to right. So you would go start at 3s. Okay, so you're going to go through those first two. So that'd be 3s2. And then you're going to land on 3p3. Okay, when you land on 3p3, that is going to be phosphorus. Okay, then we want to know what group and period would it be in. Okay, so group is when it goes up and down. Okay, so you would look at the top, and phosphorus is in the group 15/5A. So you can write it like that. And then if you look to the right, look to the left, on the very left of the periodic table, you have the period numbers. Okay, so periods go from left to right. So groups go up and down, periods go left to right, and that would be period 3. Okay, so the next one, you're going to start at argon and then go down to the next level. Okay, so start at the left, you're going to go through 4s2, through the transition metals, so 3d10, and then you're going to land on 4p4, and that is going to be selenium. Okay, so if we want to look at group number, you're going to look at the top. Okay, the top of the column for selenium, and that's going to be 16/6A. And then if you look all the way to the left, okay, your period number for selenium would be 4. Okay, the next one we give you calcium. Okay, so we did not give you the noble gas configuration. Okay, so that is what we're going to do next. So you would look at the noble gas that is right before calcium. Okay, so the last one before calcium, and that would be argon. Okay, and then calcium is when you land on 4s2. Okay, and you would look up. We're going to look at our group number. That is going to be group 2A. Okay, then our period, if you look to the left, you'll see that number. It is going to have a period number of 4. Okay, so that should be kind of a little refreshment. So the big thing here is to know that groups go up and down, periods go left to right. Number 29, write the extended electron configuration for each element. Okay, so this is when we're actually going to go through and start at the beginning. So we're not doing the noble gas shortcut. Okay, so sodium, which is basically Na. Okay, so we need to get that way. So we're going to start at the very beginning. So you're going to start at hydrogen. You're going to go through hydrogen and helium. So that's going to be 1s2. Okay, then you're going to go down to the next level. We have to go all the way through 2s2. You're going to jump across that big area. And you're going to go all the way through 2p6 because P can hold 6 electrons, okay? S can hold 2 because there's only 2 columns in S. P can hold 6 because there's 6 columns. D can hold 10 because there are 10 columns in the D level, okay? And then lastly, sodium, you're going to land on 3s1. 29, so we're going to go into chlorine. So chlorine, we have to start at the very beginning. Okay, so we're going to start at hydrogen, so we're going to go through 1s2. Then we're going to go through 2s2. Then we're going to go through 2p6. Then we're going to go through 3s2. And then finally we're going to land on 3p5. Okay, so if you need more practice on that, you can go back to some of my older videos if you want to kind of watch that more in depth. Okay, so this is just kind of a review on how to do extended electron configuration for an element. Okay, so number 30, I believe this is going to be the last one for this part of the video, so this kind of splits it in half. Draw the Lewis dot structure for each of the following elements and identify each element's family or group. Okay, so potassium, that is going to be an alkali metal. Okay, and to do Lewis dot structure, you're going to draw your symbol, which is K, and you're going to look at the top of the group. Okay, and you're going to look for things like 1A, 2A, 3A, 4A, 5A, 6A, 7A, and lastly 8A. Okay, so that is your number of valence electrons. The perfect number is 8. Okay, so K is in that first group, so it only has one valence electron. So that means we're just going to start at the top and we're going to draw one dot, and that's it. Fluorine is going to be in the halogen group. Okay, so that is that second to last group. Okay, so we're going to draw fluorine, and you would see fluorine that has 7A on top. Okay, so that means we have 7 valence electrons. So we're going to start at the top. We're going to count 1. We're going to go clockwise. 2, 3, 4. Then we start doubling up. 5, 6, and 7. Argon is going to be a noble gas. Okay, so those noble gases are the last group. Okay, so it's the last vertical column on the right. Okay, and so argon is abbreviated AR. And that, if you look to the top, it has 8A above it. So that means it has 8 valence electrons. So that's going to be 1, 2, 3, 4, 5, 6, 7, and 8. Okay, last one, magnesium. This is going to be an alkaline earth metal. Okay, and is abbreviated Mg. And if you look to the top of that group, you're going to see 2A. So it's only going to have 2 valence electrons, and so you're going to do 1, 2 dots. Okay, so this was the first part, so hopefully that kind of helped. The second part will be out soon, so you can kind of go through that. So big thing is just look for areas. If you need help on things, you can kind of fast forward to those. If you need more help, you can go back to previous videos to kind of see us go more in depth. So this is kind of just to give you a little bit of a refresher and not go too far in depth without taking a ton of time. Okay, so let us know if you need anything, and hopefully this helped.